I'm Vineeth. I'll be talking about our Big Data for Health project, which involved reproducing the results from this paper called SurfCon, Synonym Discovery on Privacy-Aware Clinical Data. So, in recent years, an increasing adoption of electronic medical records has provided us a large data set of useful information about diseases, about treatments, about patients, which can help us enhance our understanding of conditions and hopefully improve health outcomes. The challenge, however, is usually how do we generate insights from this data? So we can look at this data set with several high-level use cases or goals. For instance, we can train models for predicting risk level of patients, learning representations of medical concepts, treatment recommendation, clustering similar patients together, or indexing all the documents for effective search and retrieval. The SurfCon paper mostly focuses on the search and retrieval task at its core. However, note that several other goals can be formulated as a search and retrieval task as well. For instance, if we can search documents effectively, we must have learned a good representation. We can also search for similar patients or prior cases for recommending treatments based on this similar model. So even though the immediate goal is search, its applications may be applied to the wider possibility. In particular, the approach that SurfCon paper takes to the search problem is through discovering synonyms of medical terms. For example, in this case, a query term like heart disease may retrieve synonyms like heart attack, cardiac arrest, or heart failure. These synonyms could then be used to retrieve the referring documents or used in other downstream tasks. For example, we may want to normalize the medical notes so that the different terms with the same meaning are replaced with the same term for consistency, or we may want to cluster patients based on the similar terms. And so this general task of synonym discovery can be applied to a lot of use cases. However, the typical concern is that many synonym discovery models typically rely on the raw notes to be trained. For example, they may perform some word-to-vec like computation, and so they need the immediate context surrounding a medical term for synonym discovery. In practice, this may be infeasible due to the size of these data sets, but even more importantly, it brings to light many privacy concerns. Even with techniques like de-identification, we cannot guarantee differential privacy in most cases. So using this raw dataset might not be the best idea, but one strategy is to use a co-occurrence graph in its place. Here, each node is a medical term, and the weighted edge between them has the co-frequency count. By aggregating information in this way and making sure that the nodes with very low frequency are pruned to avoid leaking information, we can make a privacy-aware dataset for this task. Using this co-frequency counts directly, however, is problematic. Let's consider the term heart attack, for example. If you were to look at co-frequencies directly, we'd find that the top neighbors of the term are generic terms like medical history. Such terms are less informative typically because they occur so frequently as it is, that their joint frequency is less meaningful. Even after subsampling some very high degree nodes, we run into this issue where the weights will always be larger for terms whose singleton frequencies are higher. So essentially, the co-frequency is a joint probability here of P of A intersection B, but we want to modify it to incorporate marginal probabilities P of A and P of B. And so the PPMI score does just that. It modifies the raw counts by incorporating the marginal probabilities of the terms. We also apply a log and clip it at 0 to make sure that scores fall into a reasonable range because we'll be using these to train machine learning models. So are we done? Can we just use the PPMI weights to calculate the top neighbors? Well, not even close. First of all, this graph is very noisy, and co-occurrence does not always imply semantic equivalence. More importantly, though, most synonyms actually look alike, or as the authors refer to it, synonyms share some surface level information. By only considering this co-occurrence graph, we would lose all of that information. So to learn all of this, the SurfCon paper presents the first innovation. It is a common practice in general, for example, autoencoders, to learn to predict the actual data based on some compressed embedding. What this tends to do is it denoises the data because the abnormalities and anomalies of the input data are smoothed out when predicting it in this way. Further, we can construct this compressed embedding using some surface level information. In particular, the authors propose using a bi-level encoder that utilizes both the character and word level embeddings to map an input term to a surface embedding. These 100-dimensional embeddings are concatenated and projected into a single 128-dimensional embedding, which is then used to predict the distribution of the relative PPMI weights. So instead of just using the raw PPMI weights that we computed earlier, we can use these predicted ones downstream that we expect to be less noisy. One advantage to this is that it can help us generalize beyond the in-vocabulary terms. Since the surface embeddings just take the character engrams and words, the term itself does not need to be part of the graph. Another thing to note is that we could speed up training by using pre-trained embeddings here as the starting point, and that is what the authors actually do. At this point, we can use the trained surface embedding and predicted context to directly compute some distance metric against our database of terms. For example, we can compute the cosine distance across all surface embeddings in our dataset to find the most similar looking terms. In practice, this seems to already provide most of the performance gains over the baseline methods in the paper. However, note that we haven't even leveraged the ground truth synonym data yet. Perhaps by using ground truth binary labels of whether a pair of terms are synonyms or not, we can re-rank the candidate terms for even more precision. Note that when I say ground truth here, we're actually taking the UMLS CUI mapping, so any two terms that map to the same concept are considered synonyms. Before we get into this, we need to understand what the context prediction module is really doing. Note that in the co-occurrence graph, we might not just have edges between synonymous terms, but also other terms that may share a cause-effect relationship or other diseases that frequently co-occur with the query term. Similar to techniques like word2vec, similar terms may not even be in each other's context directly, but instead share a lot of the surrounding context. For example, one doctor preferred to write heart attack over cardiac arrest, whereas another one preferred the other way around. In that case, the co-occurrence relationship may actually be weaker than the fact that the other terms in the context, like chest pain and cholesterol, do co-occur with both of the terms. Thus, highly similar terms might not only share a direct edge, but often have a strong second-order relationship. The context prediction module from before will ideally put the surface embeddings for the two terms close together because the contexts in which they occur are similar. Turns out we can learn an unsupervised embedding to capture the second-order information, for example, using the algorithm called line second. So we can just use the pre-trained embedding on this weighted graph and then use it in some ranking model to utilize the ground truth labels. So this is how it really works. Each query and candidate, we first take the top K predicted context from the previous module. For example, in case of heart attack, it may be chest pain and cholesterol, whereas for cardiac arrest, it may be cholesterol and bypass surgery. Then for each of those contexts, we retrieve the pre-trained line embeddings. Now this is where it gets interesting. We perform a pairwise matching of the context, similar to an attention mechanism. I'll cover more on this on the next slide. The mechanism would essentially find weights for each of the K contexts to allow us to take a weighted sum and produce a single context embedding for the query term and a similar one for the candidate term. And then that allows us to essentially use a vector distance metric like cosine similarity or bilinear similarity to produce a single score, which we can then combine with the surface similarity score, for example, using a weighted sum, and then train this model using the binary cross entropy loss based on the positive and negative synonym samples in our ground truth data. So suppose we have a query term and a candidate term here with their top two predicted contexts. We want some way to compare the line embeddings of the context of these two terms. A simple approach is just to average those embeddings and then compute a cosine similarity, for example. The authors call this a static representation and then move on to propose a better approach. Essentially, what we would do is do a pairwise matching of each of the two contexts. So in our case, this matching function just computes the bilinear similarity between the line embeddings for each of the contexts. So suppose for the cholesterol term, we would have the similarity weights computed to be W11 and W12, which is just the bilinear similarity of the terms involved, of the line embeddings of the terms involved. Similarly, for bypass surgery, we will have two weights, and then we can average the weights for each term, apply a softmax activation, and use it to take a weighted combination of the embeddings to get a single embedding. Note that it would then be symmetrical for the query term as well. And then we can compare it using cosine or bilinear similarity. So the difference from averaging is that hopefully it would preserve some more information. So that was a really complicated way of just comparing the context, taking the top K, embedding them using line, doing a pairwise matching, and then pooling them using those attention weights. Why go through all of the trouble? Well, the authors hope that this can learn how each of the contexts of the query matches with each of the contexts of the candidate term. The hypothesis is that this strategy can better rank terms that don't look similar to each other. Now, to see if this actually works, we use the mean average precision metric. It's a popular ranking metric that'll give a ranking of elements, figure out how good that ranking is. So given a list of test terms, we measure the ranking quality on two kinds of inputs. The first input is called a random selection input, where for each test term, we take all the true word synonyms of that term and mix it with 100 non-synonyms as the input. And then we rank them using the model and use a mean average precision to measure how good that ranking is. The second is a more, in a practical scenario, this might not always work. So essentially, we find the 100 candidates using cosine similarity based matching of surface embeddings and static embeddings. So the embeddings that we computed earlier, we index all of our embeddings in a database, then match a new embedding on that entire database, and hopefully that'll give us most of the synonyms that we're looking for, and then we'll re-rank them using the SurfCon model. Now, in terms of the metrics, by and large, the authors, all of those metrics are much better in almost every case. So, for example, we get 75% in the all-day data set, whereas they get almost 90%. Now, this can be due to various reasons. First of all, there's a lot of randomness in the weight initialization, in the random selection. There's some hyperparameters that are not clearly mentioned in the paper, so we have to make reasonable assumptions, and there's more tuning that can be done in that case. But overall, and all of these metrics that we achieve are already better than the baselines that the authors cover in their paper. So even though the magnitude of the improvement that the technique provides may be overstated, the existence of an improvement is indisputable. Secondly, we see that the authors, so there's three model variants. So the surf only model is just comparing based on the surface embedding. The static model compares just based on the static embedding, and the SurfCon model is our final complete model end to end. And ideally, what the authors hope is that the SurfCon model is better than the static model, which is better than the surf only model as they increase complexity down the variants. However, we have not been able to replicate that ordering. In most cases, the improvement offered is very minor. So in this case, we get an improvement of 0.0001. In some cases, we get a little bit higher, but by and large, the improvement from going from surf only to SurfCon is not that significant. So the additional complexity and computational cost, note that because we do a pairwise matching, there's a quadratic cost in the number of contexts. That may not be worth it given that the improvement we see is so minor. However, like I said, the surf only scores are already better than any other technique that the authors compare it against. When it comes to the inference stage metrics, again, the authors outperform all of our metrics consistently, and in some cases huge margins. But again, all of our results are better than the baselines that the authors mentioned. So again, the magnitude of the improvement might not hold. It might be exaggerated, but it's definitely valuable in this domain. So in conclusion, the bi-level surface encoder, I think, is highly effective in this problem domain. It seems to beat most of the other alternatives considered at a relatively low computational cost and complexity. On the case of the dynamic context matching module, the second module which does all of this complex ranking, it adds value in some cases, but that value addition is not significant enough, I think, to justify the added cost and complexity. So that was SurfCon in roughly 15 minutes. Hopefully this was valuable. Thank you very much.